Hello everyone. In this video we're going to take a look at examples of normal random variables, sums of normal random variables, and some central limit theorem applications. So our quick outline is the first example is what I call a normal random variable comprehensive example. So number one here together with number two gives you just about everything you need to know from this section on normal random variables, at least an example of it. Example 3 covers a sum of normal random variables. And examples 4 and 5 involve the central limit theorem. One is based on a normal approximation of the binomial, and the other is based on calculation of a probability involving sample means. So we begin with example 1 here. Suppose a certain cereal is filled into boxes by weight, with a weight that's approximately normally distributed, with an average of 16 ounces and a standard deviation of 0.2 ounces. We want to find the probability that when you buy a box, think of this as a random selection, the weight is less than 15.5 ounces in A, and B, the weight's between 16 and 16 and a quarter ounces, and in 17, the weight's more than 17 ounces. So our random variable X represents the weight of a box. The probability the weight's less than 15.5 is equal to, now we transform this to our standard normal random variable. So I get 15.5 minus 16 over 0.2. That's equal to the probability Z is less than minus 2.5. To find this with our table, now the table just involves positive Z values. So we could express this as 1 minus the probability Z is less than 2.5. Look up the probability Z is less than 2.5. Now I've indicated this using a red circle on a table that you'll see here. So that would be this one right here, 2.50. That probability is 0.9938. So that's where we get this number. But we have to subtract. We have 1 minus 0.9938. We get 0.0062. For part B, we want the probability X is between 16 and 16 and a quarter. So transforming this to Z, the left bound or the lower bound, 16 minus 16 is going to give us 0. The upper bound, I'm looking at 16.25 minus 16 over 0.2. That simplifies to 1.25. So to find this, we need to find the probability Z less than 1.25. And then we need to subtract the probability that Z is, well, less than 0, which is 0.5. So we get 0.8944 minus 0.5, or 0.3944. And these probabilities are given on the table with the blue circles. Let's take a look at that. So I had 1.25. Okay, this would be my row, my 1.2 row. This would be the column. So that's where we get the 0.8944. And the probability Z is less than 0 is exactly 0.5. It's the left half of the area under the curve. Okay, so that's how we get to this answer here. For part C, we want the probability that X is greater than 17 ounces. So how likely is it that you get a box, should be 16 ounces, how likely is it you get a box that has more than 17 ounces? Well, we want to find the probability Z is greater than 17 minus 16 over 0.2. Easy to see that this fraction simplifies to 5. So the probability Z is greater than 5 is approximately 0. So it's very unlikely that this will happen. Okay, so that completes example 1. Now, in example 2, let's assume the same parameters. Okay, we're looking at weights of cereal boxes. So X has an average of 16, right? Standard deviation is still 0.2. Suppose we ask, what's the upper cutoff for the 90th percentile of weight? So think of these as weights here. Okay, and ignore maybe some of these numbers, but the key is that we want the value right here. It's the value that gives 90% to the left and 10% to the right. That's what we mean when we say the 90th percentile of weights. And in part B, we're interested in the range for the middle 60% of weights. So the middle 60% would leave 20% in each of the tails. So to find the solution for A, the first thing we need is the Z value that leaves 90% to the left and 10% to the right. So what you have to do is find the Z value that gives us 0.90. And again, on this table that I showed you, this would be the green circle. Okay, right here, the closest we could get to 0.90 is 0.8997. Okay, I know it's not exactly 0.90, but it's definitely closer than what you see here or what you see here. So we get the Z value. This is like applying an inverse function. So the Z value would be 1.28. Okay. So we can use that. Okay, we use the 1.28 to get the cutoff, which is an X. We know that X is equal to mu plus Z sigma. Mu is 16, sigma is 0.2. So when I substitute and simplify, we'll get 16.256 ounces. So this represents the 90th percentile. We could think of this as our cutoff point. Now for part B, we want the middle 60%. So the middle 60% again leaves 20% in the right tail and 20% in the left tail. So to get the right Z value, we need to find the Z value that's going to give us 80%. Because 20% in the right tail leaves 80% to the left. So as I've said here, see the yellow circle. Okay, so this would be right here. I'm trying to get as close as I can to 0.80. And you can see right here, this is it. Right, 0.7995 is the closest. This you could see is somewhat close, but not as good as this, 0.8023. So here's my value. The corresponding Z value is 0.84. Okay, so that's where I get my 0.84. And really, we could use positive and negative 0.84, okay, because of the symmetry involved here. So the cutoffs on the high end, I'd use X as mu plus Z sigma, 16 plus 0.84 times 0.2. I get 16.168, and that's ounces. The cutoff on the low end, I have a similar formula here, but I subtract. So when I work this out, we get 15.832 ounces. So these two values would identify the middle 60% of the cereal weights. Okay, for our next example, let's suppose that at a library, a student checks out 10 books, and let's say she estimates that each book has a normally distributed weight. The mean are 12 ounces, the standard deviation 3 ounces. What's the probability that the total weight of the 10 books exceeds 125 ounces. So here you want to think of 10 random variables, all normally distributed with mean 12, standard deviation 3. So this is a good problem for you to try on your own. I recommend you stop the video and try this. It's not too hard, this problem. It's not terribly easy, but it's friendly, so give it a shot. Okay, did you get 0.2981? Well, let's go through the solution. So again, the weights of the books should be thought of as independent, identical, normal, random variables. So the total weight of the 10 books is expected, right? Or this is the expected weight of the 10 books. We could get it by simply multiplying n times mu. N is 10, mu is 12, so we get 120 ounces. The standard deviation for the total weight, well, here we have to think in terms of really finding the variance first. So our formula, similar to this, applies to the variance. We know the standard deviation is 3, but the variance is 3 squared. So I get 10 times 3 squared. 10 times 9 is 90. Square root of 90, I get 9.487 ounces. Now we could work this out because we know the sum of normals is normal. So we get the probability that z is greater than 125 minus 120 over 9.487 is equal to the probability z is greater than 0.53. So we could use complements and look up the probability z is less than 0.53 to get this number. But since we use the complement, it's 1 minus this number, so we get a probability of 0.2981. Okay, moving on. Let's take a look at a problem requiring us to use the Central Limit Theorem. This is sort of sometimes called a normal approximation of the binomial. Let's say Geo is pursuing a major in computer science. He notices a memory chip containing 2 to the 12th, which is 4,096 bits, is full of data. The data seems to be generated bit by bit at random with zeros and ones, equally likely, and the bits are stored independently. So if each bit is equally likely to be a 0 or a 1, estimate the probability that there are actually 2,140 or more ones stored on a memory chip. These are just some pictures of what a memory chip looks like. All right, if we let x be our random variable, where x represents the number of ones, then x is binomial. And we could think of x as the sum of a large number of Bernoullis. So we know by the Central Limit Theorem that x behaves like a normal random variable. So we could use the normal approximation here. Because each bit is equally likely to be a 0 or a 1, the probability it's a 1 is 0.5. Right? We can think of a 1 as a success here. Probability of success is 0.5. So we expect an average of, think of this as n times p, 2,048 ones. Our standard deviation, right? Remember, standard deviation for a binomial, sigma is equal to the square root of n times p times 1 minus p. So here we get the square root of 4,096 times p well, times 0.5, and 1 minus p also 0.5. So when we work this out, we end up with a standard deviation of 32. Now we want to find the probability x is at least 2,140. But x is discrete, and if we try to do this with the normal approximation, we know the normal random variable is continuous. We need a continuity correction. So what we're going to find is the probability that x is greater than or equal to 2,139.5. Okay, so we can work this out, converting to a standard normal. I get the probability z greater than 2139.5 minus the mean, 2048, over our standard deviation 32. So that's equal to the probability z. This should be greater than or equal to 2.86. And we could work that out, getting a final answer of 0.0021. Okay, now for our last problem. Again, a central limit theorem application involving sample means. Let's say a restaurant claims that their burgers have a quarter pound of meat, right? Very famous item, the quarter pounder. Now, suppose that students measured some of these for a project and concluded that the expected weight is 0.251 pounds. Standard deviation is 0.02. After getting this information and starting out on this project, suppose the 30 students celebrate by each ordering a burger. So the 30 students all go to the restaurant, they order a burger, and let's say they weigh them, and we ask what's the probability that among the 30 students, the average weight is less than 1/4. Okay, so we're talking about 30 students. Think of the 30 students as a sample. We want to know the probability the sample mean is less than 1/4. So again, I'm recommending stop the video and try this. Now I mean try the problem, not the burger. We can do that later. Okay, did you get 0.3936? If you did, great job. For 30 students, the average burger weight should have a mean of 0.251. So here I mean this is the mean of the sample means, 2.251. The standard deviation of the sample mean, okay, well, we have to remember by the central limit theorem that it's the population standard deviation 0.02 divided by the square root of n. So here we divide by the square root of 30. So the standard deviation for the sample means 0.0037. Okay. We also know that the sample means will follow a normal distribution. So the probability the average weight of their burgers is less than 0.25 is given by the probability z is less than 0.25 minus 0.251 over 0.0037. When we simplify this fraction, we should get the probability z is less than negative 0.27. And using our table, we have to sort of look at 1 minus the probability z is less than positive 0.27. So we get 1 minus 0.6064, which gives us 3936. So this concludes the video. I hope you found it useful.